Hello, I'm David Shin, and this is Physics Lab 4, Oscillations. So this lab was intended to track the position of an object oscillating, and it follows the principles of harmonic motion, and the object moves as a pendulum. The object's motion only changes in the x and y direction, so 2D, and I used the video given in the lab instructions, and the position data was gathered through Tracker, and GlowScript was used to generate a model with the energy graphs needed. Then we compared the two models, and this lab involves the use of energy principles. So here are just some equations and miscellaneous info. You can see that we have the energy equations to the left, like the potential gravity or the kinetic energy equation. And we follow the energy principle that the change in total energy is zero, meaning that energy cannot be created or destroyed. And the model and the recorded motion are very similar in terms that they follow harmonic motion, but their amplitudes are very different, in which we'll discuss later. And we use Newton's second law, which is F equals ma, Hooke's law, which is seen below in the bottom left, and the energy principle, which I just said. Energy cannot be created or destroyed. And so the system is the Earth, spring, and the mass, and we assume there is no work done by the surroundings. This means there is no external work, and the energy is solely based on the elements within the system. The previous equations make up for everything in the system, including the spring, GlowScript generated graphs, and the properties of motion displayed. Here's our tracker video. You can see that the x amplitude stays relatively constant, but the y amplitude decreases slightly as the spring heads towards its resting length, as the spring wants to go to L naught. And so here are our initial conditions in the code. You can see that the ball's mass is 0.402 kilograms. Here are the position vectors, and then you can see over here that we just have to set gravity, the spring constant, and the relaxed length of the spring. And then here are just some calculations to find the distance of the spring from its resting position, and L hat, and then basic energy equations as seen before. Here's the code continued within the loop, actually. This is updating the velocity and position, updating L hat, and S, and also updating the energy changes, or calculating the final energy changes at the end per timestamp. And so you can see here, for these energy changes, the total energy, which is this orange line in the middle, is zero, meaning that this motion actually does follow the energy principle, even though there's lots of oscillations and things like the potential energy of the spring, potential energy of gravity, kinetic energy. You can see that the overall energy is zero. And I didn't go over it before, but here is the equation for potential energy of a spring. It was not in the equations, but here it is over here. And so here are the position graphs. Like I said earlier, they all follow harmonic motion, but these amplitudes are very different, which is described in errors later. But you can see that the y position and the x position generally follow this pattern of a sine wave, same with the y position. And the little bumps there are mostly due to errors in human errors in plotting the points. And so our model does justify the energy principle, as the total energy change is zero, and there is no outside work acting on the system, meaning that energy is conserved and the principle holds true. And so we found the period of oscillation for the x direction using the timestamps 3.704 and 5.413, which is 1.709 seconds, and the period of oscillation for the y direction, which is 3.419 and 5.033, which is 1.614 seconds. And I thought that the period for the y direction was shorter due to the spring wanting to return to its resting position, meaning that the amplitude of the spring decreases, which therefore makes the period of oscillation decrease. And for these graphs, the model generator is pretty accurate just because it does follow that harmonic motion again, but there is a large error in the amplitude, which is described in errors later. But the energy graph and the position graphs generally follow the same pattern and the laws of motion and energy. And so these sources of error, human error is the largest error in taking the position data for the tracker model, and that led to errors in calculations like the period of oscillation. And you can see that in the differing periods of oscillation as seen in the data. And there's also a large difference in amplitude gathered, which could be due to a miscalibration of data in tracker paired with this human error in tracking the data points. Thank you.